Okay, so we're going to look at some key learnings from the Desmos activity that you played around with. The activity is called Discovering Combinations of Functions. I'll put the link down in the notes. But let's see some of the key learnings that you discovered in this activity. So I imagine that most of you, actually, when I look at your answers, everyone said this looks like a linear function, like, oh, this is an easy question. And then, of course, we zoom in and very quickly discover that, oh, it's not. Something weird is happening in there. Okay, and so what this is different combinations of things to produce this graph. Now, we kind of graphed things like this before. It might look like some of the rational functions that we graphed before, but it's definitely different than what we expected when we looked from afar. So now it kind of looks like maybe irrational. Is that what people said? Yeah, it looks like rationals. Yeah. So it looks like a rational function. And the reason is that it's actually a combination of the both. So you see that this is a new function. I've called it h of x, so it's a combination of two other functions added together. You see the linear function definitely from afar, but when you look in close, you see a rational function. So we can describe this as local behavior and global behavior. And so I think that was probably something you all discovered in the activity, that locally, so if you look really close at some small x values, it looks one way, but if you step way far away from it and zoom out, like the first picture we showed you, globally it looks differently. And so this one has a global of a line and locally as a rational function. And so I could have the two functions by themselves, but when I combine them and add them together, I end up with this new function, where for the most part it looks like a line until I zoom into this part where it looks like a rational. And so you see here, I could either, using Desmos, I could say I'm just going to take the two functions and add them together, or I could actually write them out like this, but it's the same thing. Okay. Again, here we look, and if you're looking way back, it looks like a quadratic. But of course, when you zoom in, we can see locally it looks very different. It looks like another rational. So globally, kind of parabolic, right? So for the most part, the parabola is, or the quadratic is winning, but locally a rational. And again, you see the same idea happening here. If I traced over this and zoomed out, it looks like just a parabola. You can see the orange line is like virtually exactly on the green. Is it exactly on there? Well, no, because there is a little influence of this line, or this rational, but not a lot. And it speaks to some of the ideas we had before. When x is a big number and you square it, that's going to get really big. So the 5x squared is going to dominate this function. When x is like 100, the bottom's going to be 96. 2 over 96 is really small. So as x gets really big, this part of the function takes over, and this part has very little influence. It does have something, but very little influence. That's why when x is big, it looks almost exactly like 5x squared. But when it's small, well, what happens when these numbers, when x gets really, really small? 2 divided by 0.001, that's a big number, right? And so this guy takes over, and when this is 0.001 squared, who cares? That doesn't have a lot of influence. And so that's why down here, it starts to, a rational function takes over and says, no, start looking and behaving like me. because these values are going to be different. And again, you see these numbers start to look almost match up exactly to the rational function. So again, moving on, you see this one, I know we said was trigonometric, but this one kind of really surprising. And these are the ones that I love, the trigonometric ones. Like, wow, this looks completely different. What did we think this looked like? Yep, that's right. Looks like an exponential function. And so the global behavior, if we couldn't even see the little ripples in the graph, if you kept zooming out and out and out, we might have guessed that it's just an exponential function. So globally, it's exponentially. But locally, if you did zoom in, it's trigonometric. And again, here's the exponential function that's going on. And so if I zoom out, this graph looks like it's almost exactly like the red one. But when you zoom in, you start to see that's actually a trig function that's following that path. And as we get down here, you see how this is going to be really small, isn't it? 1.1 to the power of negative 60. That says a really small fraction. And so the exponential becomes less and less influential as we get down to really small numbers, and it's just behaving like a trig curve. But as x gets bigger, of course, when we start doing 1.1 to the power of 10, that's going to have a lot more weight than the sine x. So here's the graph of sine x plus x. So it's adding a linear function. It's just adding something at the end. But I want us to try and really understand why this is the case. So, and I think this is what the next few slides talk about. The plus 1, like say I was doing sine x plus 5. What does the plus 5, how does it transform, the sine x? Yep. Yeah, it just moves it up, right? So if instead of moving up by a constant, like if it's plus 5, it moves up 5, and then you have the sine curve. Or plus 7, move up and it just does that. If you're adding a function of x, as x gets bigger, the graph gets moved up more each time. So when x is 2 or 3, this sine curve goes up to 2. And then the next step, it goes up to 3. And then the next step, it goes up to 4. And so it's still trying to be like a sine curve, except it gets pushed up and up and up. And so the vertical translation is what's changing as x changes. The sine x, when x changes, it just behaves normally. But if you're going to have plus a function, then the vertical translation is going to always change. And so that's why this is going to get bigger as x gets bigger and smaller as x gets smaller. So then this was a really key understanding. What if we take that x and multiply it? Well, now that x goes out front, right? And so instead of it being sine x plus x, where it changes the amplitude, the vertical translation, if I multiply it, let's say I just multiply it and bring it out front like this, what's it changing? Yeah, the amplitude. So as x gets bigger, what should the graph do? Well, it's going to go up and down bigger and bigger. And as x gets bigger, the amplitude is going to change. And I know you've already seen what this is going to do, but now we can start predicting some of these combinations without even seeing the graph. I think you can imagine this graph getting bigger and bigger, the amplitude getting bigger and bigger. So if we actually change this to that, we get this neat shape. And you can see the amplitude starting normal, almost going up to 1 like it normally does. and then, oh, it's getting a little bigger, and then the amplitude gets bigger and bigger, and then, of course, as you zoom out, you get this really awesome looking graph. And if we get too far, yeah, our computer starts to struggle. All right, but that's what's going on here, and we can start predicting how these will look. And it's really cool that if it's being multiplied by x, you can actually see the x influence, that it's going up. The highest point is going to be the value for x, and negative x in both directions. And of course, if you change the x to not just x, but 3x, so you're making it a steeper graph, this is going to be, of course, become steeper. And then my cool one is if we change it to x squared, the amplitude is now going to follow not a linear function, but a quadratic function. And we have this really cool graph where you can see the parabola being like the boundaries of this graph. And we can actually, if you put in that quadratic, you can see it right there. And then, yeah, this is where it gets really, yeah, see, my computer's already struggling. Trying to change the amplitude to really small and big numbers. Come on, you can do it. Okay. All right. So then if you wanted, I don't know if people messed around and did some of their own creations. Did anyone come up with some? Oh, yeah. Look at this. This is interesting. Oh, cosine, and what is it going to do to cosine? That's neat. Yeah, so it looks familiar. Vivian here. Oh, cosecant. Cool. And an x to the power of 4. This is neat. Ooh, a whole bunch of sines and rationals. So that's kind of cool. Got some neat things going on there. Of course, a rational function, as it goes off, it gets very, very small, almost 0 maybe. And so the graph, the sine curve, it starts to become just like a sine curve here. But locally, some really cool pictures, especially when you get these colors going in there. So some cool stuff. All right, so that's the key learning from that Desmos activity.